Okay, so last session we defined LP spaces. Now we are going to look at the so called LP norm on these spaces. Our aim is to prove that it is actually a norm. Of course, there will be certain things to be modified. We will see that, especially with the property that if the norm of a vector is 0, the vector is 0. So, that is not strictly speaking true in LP spaces. We have to mod out the space with an equivalence relation, but that is not really going to trouble us with any kind of computation. Okay, so let us continue with the proof. So, recall that we are trying to prove LP norm is a norm actually. So, if I take f, then the LP norm is defined to be, so this is integral over x mod f to the p d mu to the 1 by p, right, but this was true for 1. So, we are looking at only p between 1 and infinity, okay, strictly less than infinity, and you have L infinity norm to be the infimum of all those functions, all those m such that mod f is less than or equal to m almost everywhere with respect to mu, of course. So, you look at all such m and then take the infimum. So, we proved the following lemma. So, let me recall that. So, lemma we proved was if I take a, b, alpha, beta all positive with the alpha plus beta equal to 1, which is a convex combination, then we have a to the alpha, b to the beta is less than or equal to alpha a plus beta b. So, this was simply a consequence of minus log being convex. So, this has an immediate corollary. Well, what is the corollary? So, I take two numbers C D positive, P and Q greater than 1, 1 by P plus 1 by Q equal to 1. So, the P and Q are called conjugate exponents. So, P and Q are called conjugate exponents if 1 by P plus conjugate exponents if 1 by P plus 1 by Q equal to 1. Okay. So, these are between 1 and infinity. Okay. Infinity is allowed. So, if P is infinity, 1 by P is 0. So, Q will be 1. Okay. So, 1 and infinity are conjugate exponents. So, if you take P and Q like this and positive numbers C and D, then we have C times D is less than or equal to C to the P by P plus D to the Q by Q. Okay. So, that's exactly this inequality here. So, we just have to look at this and then decide. So, what do? You take C to the 1 by P, okay, D to the 1 by Q, well, C to the 1 by P to the P and D to the 1 by Q to the Q. So, this will be less than or equal to, okay, maybe I should write it the other way. Okay, because alpha plus beta should be 1, right. So, my alpha is 1 by P. So, you take alpha to be 1 by P and beta to be 1 by Q. Okay. So, A and B are these quantities, right. So, these quantities are A or B, A and B. So, C to the P to the 1 by P, D to the Q to the 1 by Q will be less than or equal to. So, this is my A, this is my B. So, I have alpha times A, which is 1 by P into C to the P plus 1 by Q into D to the Q, right. So, that is all this is, right. So, this LHS is just this. So, this is a trivial application of the inequality. So, we use that. Okay. Okay. So, we will use this in the following inequality. It is called Holder's inequality. So, you have seen some cases of this, which is the Cauchy-Schwarz inequality. Holder's inequality is a generalization of Cauchy-Schwarz. So, you take 1 P less than or equal to infinity and Q to be the conjugate exponent. So, 1 by P plus 1 by Q equal to 1. Of course, we have this space x, f, mu always. Okay. So, we have a measure space with a positive measure and we are looking at the LP space on that space. Okay. So Euler's inequality says if f belongs to LP of mu, G belongs to LQ of mu, then f times G, so this is another measurable function, this will belong to L1 mu, and the L1 norm of Fg is less than or equal to LP norm of F into LQ norm of G. Okay. So recall that LP norm was defined to be, so LP norm is simply integral over x mod f to the p d mu to the 1 by p, right. The norm is always on a with respect to the measure, so that is understood. Okay. So I am not going to write the measure in these exponents. Okay. So we will just stick to 1 and p. Whenever there are two measures etc., we will be very clear about what it is. Okay. So proof. So we use the earlier inequality. So let us look at this inequality. So we use this. Okay. So CD is less than or equal to, so I can, let me write it here, C times D is less than or equal to C to the P by P plus D to the Q by Q, right. 1 by P plus 1 by Q equal to 1. So we use that. Okay. So if we use that, we will get mod f of x by LP norm of f, okay, times mod g of x divided by LQ norm of g. This is less than or equal to, I'll explain after writing down, mod fx to the p by p times norm f to the p plus mod gx to the q divided by q times norm gq. Okay. So let's do this. So let's look at this carefully just to see if it is okay. So this is my C, okay, this is my D. So CD is less than or equal to C to the P by P. So what is C to the P by P? Well, C to the P will be, so I should put a P here and I should put a Q here. Okay. Well, I can assume everything to be norms to be 1, but let's not worry too much about it. So C to the P will be mod f to the P by LP norm of f to the P. See, remember f and g are in LP and LQ. So these are all finite quantities. Okay. So can divide by them, there is no problem. These are numbers. Now f and g are measurable functions. So for some x, mod f x can be infinite. But recall our one of the earlier results where we did, if f is in LP, so that means mod f to the P d mu is finite, which would imply mod f to the P is finite almost everywhere, right, almost everywhere with respect to mu. If it is infinity on a set of positive measure, when I integrate I will get infinity, but finiteness implies that this cannot be infinity on a set of positive measure. So except on a set of measure 0, f of x, g of x, everything should be finite. So I can choose those x. Okay. So this is fine. Now I apply, so integrate. So integrate to get. So if I integrate, what do I get? Well, this is a constant, this is a constant. I have f and g as variables, right, with variable x. So these constants come out. So I'll have norm fp, norm gq. So these are constants, they come out, integral over x, mod f into g, right, mod fx gx. So that is mod fg d mu, right, that is the left hand side. If I integrate with respect to mu, this is the left hand side I will get. Okay. This is less than or equal to 1 by p. So in the first component I have 1 by p and LP norm of f, that comes out, and integral over x mod f to the p d mu, right. So, that is the first term, plus 1 by q times norm g q to the q integral over x mod g to the q d mu, right. So, all I have done is integrate, because the functions are bounded like this, mod f mod g is less than or equal to something, the integrals will satisfy that, right, monotonicity of the integral. So, this is true. Well, so what is the right hand side? Let us look at this once again. This quantity is simply the denominator, right, because the LP norm is the one pth root of whatever is in the bracket, and similarly for this. So, this is simply 1 by p plus 1 by q, which is 1. So, now you can take this to the left hand side. So, I will get integral over x mod f g d mu is less than or equal to LP norm of f into LQ norm of g. Okay. So, this is true for 1 less than or equal to p, strictly less than infinity, okay, because we have taken, we have divided by p and q and so on. So, infinity is not included there. So, the proof works only for that. But if one of them is infinity, this is trivial. If p equal to infinity, then q will have to be equal to 1, right, because I have 1 by p plus 1 by q equal to 1. Okay. So, then Holder's inequality is very trivial. So, let us see what is the Holder's inequality. So, I look at f in LP, which is L infinity of mu, then g is in LQ, which is L1, right, because q is 1. So, p is infinity and q is 1, okay, and product is in L1, that is what we want to prove. So, you look at the product of f and g d mu. Now, you see f is in L infinity. What does that mean? The L infinity norm of f is finite. Okay. So, check. So, this is something which you should verify. Mod f is less than or equal to L infinity norm of f almost everywhere, right. So, in other words, the mod f is a function, right. So, in other words, if I look at all those points x in x, such that mod f of x is strictly less greater than L infinity norm of f, this has measure 0, okay, because L infinity norm is the infimum of m such that mod f is less than or equal to m almost everywhere, okay. So, that is why this is true. So, f is less than or equal to L infinity norm of f almost everywhere. So, I can take that outside, right, and I will have integral over x mod g d mu, which is the L1 norm of, right. So, this is L infinity norm of into L1 norm of g. So, if you multiply two functions which are at conjugate exponents, then the product is in L1. So, this is something which you, as I said, it is a generalization of Cauchy-Schwarz inequality. So, when p equal to 2, q is also equal to 2, then Holder's inequality is called Schwarz inequality, Cauchy-Schwarz inequality is the Cauchy-Schwarz inequality. Well, why is that? So, let us look at the case which is the finite dimensional vector spaces and so on. So, if I take x equal to 1, 2, 3, etc. n, then p equal to 2 norm. So, if I take a point here, so that is a vector, right. So, a1, a2, and a function on x is an n vector, okay. What is the L2 norm of this? This is the usual Euclidean norm, summation mod aj square j equal to 1 to n to the half, right. This is my Euclidean norm. So, what does Holder's inequality say? I take two functions, so a1, a2, etc. an, right, and another function b1, b2, etc. bn. You multiply them. So, this is my f, this is my g, right. So, what is fg? Well, fg is a function on x, right? So this is a function on x taking values in the complex plane. Fg of 1 will be f1 into g1, which is a1 into b1, right, and so on. So fg of n will be fn into gn equal to an into bn. So you simply multiply pointwise, right, that is your fg, and you take the L1 norm. So summation mod aj bj j equal to 1 to n. So this would be the L1 norm of f times g. This is less than or equal to j equal to 1 to n mod aj square to the half, that is the L2 norm of f, right. So this is L2 norm of f times summation j equal to 1 to n mod bj square to the half, right. This is L2 norm of g. That is the Holder's inequality, and that is the Cauchy-Schwarz inequality, you know. Okay. But in general we have, so this is the Cauchy-Schwarz. So Holder's inequality for p equal to 2 equal to q, when p equal to 2 q equal to 2, right, because q is the conjugate exponent. In general we have this to be less than or equal to summation j equal to 1 to n mod aj to the p to the 1 by p and summation j equal to 1 to n mod bj to the q 1 to the q 1 by q, right, 1 by p plus 1 by q equal to 1 less than p q strictly less than infinity. If one of them is infinity, you take the maximum out, right. So if one of them is, so maybe I'll denote that as well. So this is less than or equal to, I can take the infinity norm of let's say aj, so that is the L infinity norm of f times whatever is remaining is the L1 norm of. So these are all trivial in the case of finite vectors like this, and this is true in general is what Holder's inequality tells you. Okay. So this is the Holder's inequality. So Holder's inequality implies what is known as Minkowski. So we still have not proved that LP norm is actually a norm. So we'll do that in the next two proofs. So the next one is Minkowski's inequality. Minkowski's inequality, which will tell us that it satisfies the triangle inequality. So I take f g in LP. P is fixed between 1 and infinity. It can be infinities, okay, but infinity proofs are generally much easier. Then the LP norm of f plus g is less than or equal to LP norm of f plus LP norm of g. So there are many things here. One is that it satisfies the triangle inequality. Next, but you have to say that if f and g are in LP, then the sum is in LP. Okay, so LP mu becomes a vector space. So let us start with that. Okay, so the first part is very easy. So you look at mod of f plus. So what is f plus g norm? So you are looking at mod f plus g to the p integral over x d mu, right? This is what you want, and you want to say that is finite, and you have this inequality. Okay, so we look at f plus g. Okay, so mod f plus g, well, this is of course less than or equal to mod f plus mod g, right? At any point x, this is what will happen, but I need to take the power p. So this is of course less than or equal to the power p here, which is less than or equal to, I can replace each of them by the maximum. So you look at maximum of mod f and mod g, which means you are looking at each point. If I take a point x, mod of fx plus gx to the p is less than or equal to maximum of each of them, you replace by the maximum and then multiply by 2. So f is replaced by the maximum of f and g is replaced by maximum of f and g, and so you have the power p, right, which of course is less than or equal to 2 to the p, and the maximum is of course less than or equal to mod f plus mod g, right. So this is fine, and this implies that if I integrate with respect to mu now, This is less than or equal to 2 to the p times integral over x mod f to the p d mu plus integral over x mod g to the p d mu. And so this is finite, right, because I know this is finite because g is in LP, I know this is finite because f is in LP, and so this implies that f plus g is in LP. So if f and g are in LP, then f plus g is in LP, and you can multiply f with a constant, that constant comes out as modulus, right, from the norm. So all this discussion simply implies that LP mu is a vector space. It's a complex vector space, right, and the norm is defined on that, right. So I know that f plus g is there, and if I multiply by alpha, I still land there. That is a trivial thing. Okay, so now our aim is to prove a Minkowski's inequality. So we want to look at the LP norm of f plus g. I want to say it is less than or equal to LP norm of f plus LP norm of g. Okay, so this doesn't give us exactly what we want because of the 2 to the p here. Okay, so we have to get rid of that. For that we use Holder's inequality. So write mod f plus g to the p, right. So this is equal to, I can write this as mod f plus g times mod f plus g to the p minus 1. Okay, so remember p is between 1 and infinity. P equal to 1 case is trivial, so I'll leave this to you. P equal to 1 is trivial because that is mod f plus g is less than or equal to mod f plus mod g, and you simply integrate, right. Trivial because mod f plus g is less than or equal to mod f plus mod g. Okay, so then you integrate and you will get L1 norm of f plus g is less than or equal to L1 norm of f plus L1 norm of g. Okay, so now this is less than or equal to, so here I know this is less than or equal to mod f plus mod g. So I get two terms, one is mod f into mod f plus g to the p minus 1 plus mod g into mod f plus g to the p minus 1. So all I have done is to distribute mod f g to the p minus 1 to two terms. Okay, so now the point to note is that, so this function I claim that is in LQ. So claim mod f plus g to the p minus 1 is in LQ. I want to apply Holder's inequality. For Holder's inequality I need two functions, one in LP, the other in LQ, where 1 by p plus 1 by q equal to 1, right. I claim this. Okay, so let us see why is that true. If I look at the LQ norm of this function, so I will be taking the qth power of this, right, and then 1 by q. So I will forget the 1 by q for the time being. I want to know if this is finite, if this integral is finite. Well, this integral is simply, I have of course mod f plus g to the p minus 1 into q. So what is p minus 1 into q? Okay, let us compute that. Well, we can compute that because I know that 1 by p plus 1 by q equal to 1. Correct, p and q are conjugate exponents. So 1 by p plus 1 by q equal to 1. What does this mean? This means p plus q is equal to p cube. I want to compute p minus 1 to the q into q, right. So p equal to pq, I take the q to the right hand side, so I will get minus q, which is p minus 1 into q. So p minus 1 into q is simply p. So this is simply p. So this is equal to integral over x mod f plus g to the p, which I know is finite because f and g are in LP. So f plus g is in LP, right. We just proved that it is a vector space. So the claim is true. Okay. So now you look at these two terms. I am multiplying two functions, apply Holder's inequality. Okay. So I will write that step once more. So mod of f plus g to the p is less than or equal to mod f into mod f plus g to the p minus 1 plus mod g into mod f plus g to the p minus 1, same quantities, right. So this is in LP, this we just proved that is in LQ, this is in LP, and this we just proved that is in LQ. Okay, so we integrate and then apply Holder's inequality. So hence integral over x, remember we are trying to bound the LP norm of f plus g. Okay, so this is less than or equal to, so we will put the 1 by p later on. So I have, well, I simply integrate first. So I have mod x over x mod f times mod f plus g to the p minus 1 d mu plus integral over x mod g mod f plus g to the p minus 1 d mu, right. So now we can apply Holder's inequality because they are in the correct spaces, conjugate exponents, right. So by Holder's inequality, this is less than or equal to integral over x. So the first one will give me mod f to the p d mu to the 1 by p into integral over x LQ norm of the second function. So mod f plus g to the p minus 1 to the p, right. So into q d mu to the 1 by q, correct. So this is simply the Holder's inequality in the first term, plus again the second term will be exactly similar with f and g replaced, right. So mod g to the p d mu to the 1 by p into integral over x mod f plus g to the p minus 1 into q, right. You have to take the LQ now, d mu to the 1 by q. Alright, so this tells us that, so if I look at this inequality, what is the left hand side? You look at f plus g and you look at the LP norm and take the power p, right, because here there is no 1 by p, so that is why you have the power p. This is less than or equal to LP norm of f, okay, that is this part, and you have mod f plus g to the, so I'll okay, let me write it, f plus g to the p norm to the p by q plus LP norm of g into LP norm of f plus g to the p by q. So now you can, so this is a common factor here, you can bring this to this side, right, it is the same quantities. Okay, well, okay, so maybe I didn't explain this part. So how do you get this? P minus 1 into q equal to p, right. So here I will be writing p, but I have to write 1 by p and then cancel it with another p. So that is why I get p by q power. Okay, so that is a trivial calculation. So these quantities you bring it to the left hand side. So remember, these are all finite. If it is 0, there is nothing to do. Okay, so we'll leave that part. If f plus g is 0, we have nothing to do. So we'll assume that it is a positive quantity and bring it to the left hand side. We will have the LP norm of f plus g. I have the p here and I'm dividing by whatever is on the right hand side, which is f plus g to the p by q, right. So that would be p minus p by q, right. This is the left hand side we will get. This is less than equal to LP norm of f plus LP norm of g. But what is p minus p by q? So p minus p by q equal to p minus, sorry, p you can take outside. So it simplifies very fast, p into 1 minus 1 by q. Remember, 1 by p plus 1 by q equal to 1. So 1 minus 1 by q is 1 by p, which is 1. Okay, so that is all we want on the left hand side, right. So that is the LP norm of f plus g is less than or equal to LP norm of f plus LP norm of g. So that is the triangle inequality for the norm, right, triangle inequality. Okay, so there is a small point which I should emphasize on. So if I look at, so the same proof works. So for p equal to infinity, I'll leave it as an exercise. Okay, so this is a trivial exercise. So let's go back to LP x f mu. So I have all those functions f such that the LP norm is finite. So p equal to infinity is included, but I will not keep writing it as finite. So what do we know? We know it's a vector space. So this is a complex vector space, and we have defined the norm, right? So we want to say it is actually a norm. So let us see why. So first thing is, so there are three properties. One, okay, LP norm of f is positive, okay, and f equal to 0 if and only if LP norm of f is 0. This is what we want for the norm, right? But this is not entirely true, because if I look at mod f p d mu is 0, then all that I will get is mod f to the p is 0 almost everywhere. So remember that property that we have something, a positive function integrating to 0 will give me only integrand is 0 almost everywhere. So it's not entirely equal to 0. Okay, so we have only this much there, but that is fine. 2, we'll see why. So if alpha is a complex number and I look at alpha times f p, this I know is mod alpha times LP norm of, right? And we have the third property, the triangle inequality. I take two elements in LP, I know that it's LP norm of the sum is less than equal to sum of the LP norms. Okay, that is the Minkowski's inequality. So the only property which is missing from the norm is the first one. Okay, so all that we do is we identify functions which are almost everywhere. Okay, so LP space, so this becomes a norm, on LP provided we identify functions which are almost everywhere. Functions which are almost everywhere, equal almost everywhere. Functions which are equal almost everywhere. Okay. So we want to identify 0 and functions which are 0 almost everywhere, but we can do this for all functions. So what does it mean? So we define an equivalence relation. F is equivalent to G if f equal to G almost everywhere. Okay, and then you look at the space LP quotiented with that thing, which means that this will have equivalence classes, right? So you decompose LP with respect to the equivalence relation. So this would be equivalence classes of f, right? F is in LP. So that is the space actually we are looking at. On this space, if I, so what is the equivalence class of f? So this is all those G in LP which are equal to G or equal to f almost everywhere. Okay, so equivalence class of the constant function 0 would be all those G in LP such that G equal to 0 almost everywhere. But if G equal to 0 almost everywhere, the LP norm of G is 0, right? Because when you integrate, you don't distinguish between almost everywhere functions. So that is why G will be considered as 0. So after this identification, this becomes a genuine normed linear vector space. Okay, but we will not bother too much about this equivalence relation, because for all practical purposes we can deal with it as usual function spaces. Okay, so we will stop here. We have defined the function space called LP spaces, and we have proved that the natural norm on that space is actually a norm provided we identify functions which are equal almost everywhere. So the next step will be to study this spaces a bit more in bit more detail. We will see that they are actually complete metric spaces with respect to this norm. So remember, the norm gives you a metric. If I take f and g, the distance between f and g is the norm of f minus g. With respect to that metric, these spaces are going to be complete, and if X is a nice topological space like Rn, we will see that continuous functions with compact support will be dense in this. So, we will look at some examples in the next after proving the completeness. We will try to get some idea about these spaces by looking at some examples in the next lecture.